Hi, differential equations, method of separation of variables. Example number 1. Using the method of separation of variables, solve dp over dt equal to zero point 0.6 times p. To solve this expression, we need to know an integration where integral of 1 over x dx should be equal to log e to the base modulus of x plus a constant of integration c. This is actually coming from the general expression integral of f dash x over fx dx equal to logarithm e to the base modulus of fx plus c, where fx is the denominator here. If you differentiate denominator, it will become f dash x. So if you have an expression where f dash x divided by fx dx, then the answer to this integral is log e to the base times modulus of the denominator plus a constant of integration. In this particular case, x, when you differentiate, it will become 1. So it's 1 is differential of x. So f dash x divided by fx dx. So equal to log e to the base fx. Log e to the base, in the case of this one, fx is equal to x. So it's log e to the base x plus c. So we need to use this one in this expression here to solve. And also we should know something very basic here. E to the power a plus b is equal to e to the power a times e to the power b. So that means if the exponent is addition here, it will be a plus b, then it will become a multiplication when you separate this out. So let's see this expression that is given here. So how do you do this one? There are two variables here, p and t. So to separate the variables, what you do is take p into one side, that means dp, and take this p to this side and take this dt to the other side. So dp over p is equal to 0.6 times dt. It's called separation of variables. So variable p is in the left hand side, variable t is in the right hand side. Now what you do is you integrate both sides. You integrate and integrate. So when you integrate both sides, so you have something like 1 over p. If you write this one again, it's like integral of 1 over p dp is equal to, we can take the 0.6 out, 0.6 integral of dt. So we need to make sure that you know this expression here. When you integrate just 1 here, it will become the variable here t, and this is the one that we saw just now in the previous slide, 1 over p dp. It will become log e to the base p e to the base fx, actually it's a modulus p, equal to 0.6 times t. So if we integrate this one, it will become t plus a constant of integration c. Also you should know that if you have a logarithmic here, log e to the power x equal to y, something like that, we can write e to the power y is equal to x. So we can take off this log term by taking e to the power y, which is equal to x. This is also a known formula. So if you apply this one here, then what will be the value of p? P will become equal to e to the power 0.6 times t plus c. You have a exponent 0.6 t plus c. This is basically a one term here. So e to the power is like y here. So you take the whole thing to the power of e. So we can write this one as e to the power 0.6 t times e to the power c. And if you say if t t is equal to 0, then p is equal to p0, we can write p0 is equal to e to the power, you put t equal to 0 here, so this will become e to the power 0 times e to the power c. So e to the power 0, because t equals 0, so this will become 0. So this term is equal to 1. So that means e to the power c is equal to p0. So 1, this term is 1, so it's e to the power c equal to p0. Therefore, the answer to this question is p is equal to, this term will become equal to p0. That's what we saw, because when t equal to 0, p become p0. So this is given. So therefore, we can write e to the power c equal to p0. So you substitute this p0 in here. So that means you can write p0 times e to the 0.6 t is the answer to this question. So make sure that e to the power c can be written in the front here. So this is a constant, so you can take the constant to the front, and that is the answer to this question.